Dzień dobry Państwu. Jestem pracownikiem Wydziału Mechaniki i Robotyki, Inżynierii Mechanicznej Robotyki. Jeżeli pozwolicie, myślę, że lepiej będzie rozumiane, jeżeli mówię po angielsku, to w sumie to nigdy nie zgłosiłem to. Tak, jestem Polakiem, ale też Włochem. Urodziłem się we Włoszech, więc to ciągle mam problemy z polskim. Thank you for inviting me here. What I would like to present you is a rather not very new work, but it's dated back to 2013, and it was carried out at DLR, at the German Aerospace Center in Munich, and it concerned with the sort of uncertain analysis of planetary rover, mobility of planetary rover, a very important problem in planetary exploration. A very important problem in planetary exploration is the mobility. The mobility because of the Mars soil or as well as lunar soil is composed of mainly of regolith, which is a very soft soil, so the rover can be trapped into a region of very soft soil. So within the framework of the European Space Agency project ExoMars, DLR was responsible for carrying out the mobility analysis of the rover. And again, this is this presentation focuses on this part of the mobility problem, assuming uncertainty for soil parameters. And then at the second part of the presentation, I would just like to spend a few words about scientific activities in our department, as well as some didactic activities in our faculty. So the problem that I've already mentioned is the fact that the soft soil can be a very harsh environment for a planetary rover. There are several examples of hard mobility for NASA rovers. Maybe the most famous one is the case with the Spirit rover that got stuck in a region of very soft soil in 2009, and then it died. Most of the wheels were buried into this soil, and then the mission soon ended. So aware of this problem also before from previous missions, the European Space Agency, with its ExoMars mission, started to perform a quite detailed mobility analysis, and it commissioned the DLR Institute in Munich to perform this kind of analysis. So the institute created a test bed. You can see in the picture, maybe. Okay, maybe the movie I can show you at the really end. Yes, and also as well as a very enhanced model of the rover dynamics, including the contact of the wheel with the soil, which is a very highly nonlinear problem and hard to describe numerically. So the state-of-the-art current modeling approaches for wheel soft soil contact are basically three. The first one is based on a finite element method, but first is time consuming, is not accurate at all because there is a large deformation of the mesh, so there are many limitations on that. The second is a semi-empirical approach, which is based on some relationship where parameters are to be tuned basically based on experiments without a very deep physical meaning. And the third, that is maybe the more promising one, is the discrete element method that relies on a description of creation of particles describing the grains of the soil. But this is currently, although there is a huge development in numerical technology, introducing also graphical cards for parallelizing the process, is very time consuming, as not feasible for real-time applications. So currently the most used method is based on this semi-empirical approach that was developed by a Polish researcher, engineer, Mieczysław Becker, that during the Second World War emigrated and moved first to France and then moved to Canada and finally, eventually to United States, where he took part to lunar mission. During this time, he developed a theory where he imposes some relationships between the stress and the formation of the soil. Based on these three equations, there are some adaptation enhancements, but basically the idea is to create these kind of relationships. And based on this relationship, numerical models can be created. One of these is the soil contact model that was prepared in DLR. It is enhanced in the sense that usually these kind of models do not describe the formation of the soil, while this model is based on a creation of DEM, so-called the digital elevation map. So the soil is described in terms of a grid, and the position of the grids can be moved vertically, such to also describe the soil relocation, as well as the bulldozing effect. The multipassing bulldozing effect is the additional resistance to the movement, which is caused by the relocation of the soil in front of the wheel. But when using this model, there are still big issues which are concerned to the uncertainty to tune these coefficients here. There are several coefficients here, 7 or 8, depending on the model, and so these coefficients are calculated based on vivameter tests that were proposed also by Becker. They are of the kind of a pressure sinkage test or a shear test, where a plate is dug into a soil, and then the pressure is measured, and the deformation of the soil, the sinkage is measured as well. And the other test is putting again this plate into the soil, is also rotated to calculate the shear stresses. So the point is that there are large uncertainty associated with these parameters that are really sensitive as well to the preparation. So these experiments, as you can see in the picture, this is the vivameter device, are performed putting the soil into a beam, but this soil has to be settled before, so there is like a preparation procedure that is not very repetitive. It's very difficult to obtain exactly the same conditions. This is one part. The second part is the uncertainty connected with the, if we want to use the model as a prediction tool, so for predicting the rover path, and then we should also know the values of these coefficients along the path of the rover. This is the additional source of uncertainty. So what we performed at the institute was that's the test rig prepared. This is the rover mock-up. This is a bin filled with a rather soft soil. They are the coefficients soil parameters calculated through the vivameter test, and trying to assess a scenario that is similar to the one that could be experimented by the rover. In this experiment, we see that we have a large uncertainty for parameters. So if you try now to propagate through this computer model this uncertainty, we obtain uncertainty for the position of the rover as well. And this is a standard procedure that can be done using Monte Carlo simulation. For instance, this is a common approach. What I perform is a bit more enhanced. It's called polynomial chaos, but the idea is always the same. You have uncertainty for input parameters. You propagate through the model to find the uncertainty of the output parameters that in this case are the position of the rover. And then using, for instance, this polynomial chaos uses a probabilistic description of the input uncertainty, so they are PDFs, probability density function uniform, because we thought it's the best way of characterizing this uncertainty. This uncertainty results into this probability density function. These contour plots represent the probability density function of finding the rover position using a numerical model, so this soil contact model, which is a full rover model. This is the experimental solution. Yeah, so we performed first the experiment. We recorded all the servo data, and then we reproduce, so actually each wheel had an encoder as well as one encoder for the yaw angle. And then these data were fed into the model. So what we expected, having a correct description model of the soil contact, is to find exactly the same position. But this is what the result. After only 30 seconds, after 80 seconds, you see that the predicted position is very far away from the actual one. And another approach of propagating uncertainties through the interval analysis. Interval analysis just needs the information of the ranges. What you obtain is, again, a very large uncertainty. So what was proposed in this in one application that was proposed is the usage of machine learning-based approaches, and Bayesian identification is one of these approaches. And the Bayesian consists of in identifying the probability based on some initial knowledge, which is called prior knowledge, plus some additional data that may came across during the operation or may come from other considerations. So the prior knowledge is then augmented with this additional data, and then the uncertainty is corrected. So in our case, the additional knowledge came from so-called single wheel experiments. So we don't use only vivameter tests for calculating the parameters, but also experiments of a wheel running on a wheel, a single wheel. And then this is a more realistic scenario, of course, and then we can correct our data. This is the identified parameter from the prior knowledge, so it means the uncertainty assumed for polynomial chaos is this green one, so very large. After updating the parameter using a Bayesian approach, you obtain a reduced uncertainty that results in a much better description of the rover position, especially when compared with the polynomial scales results. Yeah, that's very short. Concludes my, let's say, almost concludes my presentation. What we realized is that there is actually nowadays artificial intelligence, as you know, is an emerging field. So I think that there is a lot of room for applying this computer-based artificial intelligence also to space sector. And with a doctor from another faculty, Paweł Zagórski, we have a strict collaboration. We have some experience in nanosatellite attitude determination and control, and then we try to also develop, let's say, or to investigate this field of applying these strategies also to control satellites, control nanosatellites, control. We have to focus on small things, as Professor Severin said. So we have also some capabilities of some small labs. Some of you have already seen that. Okay, it's not working. We can model the Earth magnetic field, the free rotation of a satellite. And also we have some didactic activities. Professor Severin is also one of the lecturers. At the moment we have one course which is called Nanosatellite Attitude Determination and Control, which is proposed within the framework of AGH International Studies, so that it's open to all of you. Whatever is your faculty, you are honored having Carol as one of the lecturers. We plan to run a new subject in 2000 on aerospace engineering. We are supervising several students with space-related topics, also offering some internship to DLR, supervise master thesis also to CDK if you like. That's all. Sorry for